Good morning, everyone, here in Silicon Valley, 11th Cloud Expo, day 4. What a journey it's been. Good morning, good afternoon, good evening if you're joining us out there on the World Wide Web. If you're joining us on the World Wide Web for this keynote, and you don't come from your hotel room, if that's what you're up to, you're not going to be able to go away with a car. So come down wherever you are, because you have to be present to win the draw after this keynote. I say no more. We'll return to that in a bit. Much more importantly, let's focus on the only perfect storm that we're all happy about, the cloud computing perfect storm. Let's give it up, please, for Lou Tucker, VP and CTO of Cloud Computing at Cisco, and let's have an amazing keynote.
Thank you so
Thanks,
much.
Lou.
Thank you, Jeremy. Well, welcome everyone. What we're going to be talking about today is this perfect storm in terms of how the internet's changing, cloud computing, and a lot of the new technologies that are coming into play. And since it's such a broad topic, I'm actually not going to be able to go into very much depth in this. But please think of the questions that you have, come up to the microphones or get them where we can pass them out to you, because I would love this to be much more interactive. Believe it or not, I'm one of those speakers who would find it a lot more challenging to hear questions from you and to have sort of death by PowerPoint here. So yeah, we are in this perfect storm around cloud computing, and it is important, I think, to realize what the major drivers are of cloud computing. Clearly, it's the growth of internet usage. As broadband penetration continues, voice, video, everything's going over IP, more and more of our services are going into this cloud. Mobility, wireless, on any kind of device. If you're actually in the content distribution business today, you know that just serving a PC is no longer enough. You have to be able to reach people on their iPhone, on their iPad, or on any device possible. We also, I think, are very much at one of these tipping points or inflection point in terms of Moore's Law. As we know, we're continuing to drive down the costs, but that means that also everything is really becoming digital. We are digitizing the world at an ever-increasing rate, and so we're seeing an explosion in number of applications and in data. In fact, I think apps now are everywhere. We have the common expression, there's an app for that. And if you look at the hundreds of thousands of applications that we now have available, and because we have such a broad distribution possible through mobile devices and everything else, those apps can be free or for 99 cents, a very small monetary value, because you can monetize that across a very large distribution chain here. They also are increasingly involving video and communications. This is where we're seeing, WebEx meetings, GoToMeeting, and other kinds of collaboration environments where we're using the internet just very naturally to collaborate and get our jobs done. And we're seeing a lot of SaaS applications, particularly like Salesforce.com, and the App Exchange, where now we have a whole marketplace of applications that are able to be distributed from the cloud. At the same time, now data is getting big. We talk about big data, and in big data, we talk about volume, the massive amount of data that we have in the cloud today, and the velocity, meaning that the speed at which that data is being generated and the speed at which we want to be able to analyze that. So real-time stream processing becomes really important. Customer buying behavior becomes important. We are able to learn so much more about our customers based upon their behavior if we can analyze it and provide a feedback loop to be able to give them an offer or adjust a service accordingly in near real time. Systems also generate an awful lot of data, and this is where Cisco, we're looking a lot at this in terms of the amount of information that systems are generating and being able to process that in real time, because as the network is dynamically changing according to the different applications and load and usage patterns, the characteristics of the network can change. Lastly, the old models of storing data just don't work anymore. When you've got billions and billions of objects you're trying to store, analyze, and everything else, the traditional database approaches don't work. So we're seeing NoSQL kinds of approaches. Object databases are rising up. And a lot of things are moving in memory. Again, Moore's law is changing some of the economics of this so that we're actually having processors going faster and faster, and data is further and further away from that processor. So in fact, what we've had is new tiers being created in between the disk and the processor. So we're seeing SSDs, which again, because of Moore's law is driving down the cost of those SSDs, we're able to use them in in-memory databases very effectively. The other thing is that this is also now affecting networking. In fact, maybe networking was sort of the last thing to be directly affected by this, is that we're seeing an awful lot of now changes in how the traffic, how network traffic appears both in the WAN and in the data center itself. People in the networking world often talk about this shift from north-south traffic, meaning from a server out to a customer's device or a laptop or something, to within the data center. Much, much more data now goes east-west within the data center. And if you think about it for a moment, of course, because a typical example, if you're making a search query on Google or something, you may have 200 servers involved in that for that one query. And you'll get back sort of a couple of pages. So there's a lot more interaction taking place within the data center itself, which changes the characteristics of the network traffic within that. The edge of the network's also changed. With virtualization now, we, instead of having a network that would have an endpoint at a host, now that host has 10, 20, or 30 virtual machines within it. So there's now virtual switches, software switches that exist now within that host. So the edge of the network's now moved to the virtual edge of the network inside of the host. And we have now the same issues around needing to manage that or apply security constraints around everything else in terms of managing that virtual switch that is now embedded inside of the hypervisor on the host. Network services also are now becoming virtualized. So this whole world is changing in terms of increasingly things are becoming software-centric, we're becoming virtualized, and they're becoming dynamically deployed. This means that, in fact, for many operators and everything else, this is much, much more complex than it was before because of the scale and diversity of things that are happening. So one of the responses for that is to try to now consequently simplify it through abstractions, and that's going to be most of the talk today about what are those ways that we can simplify this increasingly complex world so that we can operate it and provide the services that we need to. One of those ways is that we start to virtualize the network itself through overlays and tunnels, logical networks that are created on an application basis, which is an easier construct now for an application provider to think about than the entire complexity of the database, of the data center itself. So it's important, I always come back to these two guys. Gordon Moore, Moore's law, the endless sort of, it's surprising that it's maintained the same path that it's been on now through successive generations of processors, but we're continuing to drop the cost of computing by half every 18 months. And it looks like we're going to still be on that for quite a while. As we're doing that, we use more and more of it. So it's been very interesting to see. You would think that, therefore, there are going to be fewer servers sold every year because of Moore's law. In fact, there are more because we're finding more and more uses. As the cost of computing drops, we find more and more uses for computing, and we start applying it to more areas than ever before. And part of that is that now the economic side of that is that in terms of Adam Smith, we think now there's a marketplace. In fact, one of the interesting phenomena, I think, is that now we actually have a market price for computing. Computing is becoming a commodity. We can have a spot price for it. Amazon, you can use spot pricing to get virtual machines. A virtual machine market price today is essentially less than 10 cents per hour. And so now there's a whole market economics that are being applied to cloud computing, which coupled with Moore's law creates this new kind of way to think about computing with an economic basis associated with it. And of course, this guy, Darwinism. What we're seeing also is that we'll see a lot of variety, we'll see a lot of experimentation, and we're going to see selection of the different technologies going forward. So as someone who's looking to make investments in cloud computing or recast your data center into a cloud computing platform, it becomes really important for you to think through what are these trends, what are the things that you're going to bank on, And be careful of running after the newest shining object you find out there, because there will be a Darwinian evolution applied to this, and there will be winners and there will be losers. What I'm hoping is that at the same time, what we're seeing, though, are the general patterns. As a software designer and architect more than anything else, I'm always looking for what are those design patterns, because those are the things that are long-lived. And it's actually rewarding today to think about, despite the number of variations that we have in cloud computing, whether you're talking about a private cloud, public cloud, healthcare cloud, the general design pattern for how we deploy a cloud platform is essentially the same. And that's great, because that shows that there seems to be a common theme here that we're arriving at in the industry today. So let's take a look at the data center and talk about its evolution. Initially, data centers are sort of designed, you have a top-of-rack switch, you've got a lot of servers there, and it's organized, as you can see, for north-south kind of traffic as we're moving information in and out of this data center. It's generally limited in scale. It's very hard to move this, and in terms of moving virtual machines from one rack to another, that's often difficult. Recently, there's been a lot of work around fabric networking, fabric-based computing, unified computing, a lot of different terms that are used here, where we're really talking about a much more flexible interconnect so that you can have mobility between different hosts that are running these virtual machines. It also allows us to go to much larger scale. And this allows us to have a much more general model of the infrastructure and separating that a bit from the application. What we're moving to today, I think, more than anything else, and that was an application-driven data center. Meaning that what if nobody really wants to run a data center? What they're trying to do is get their applications to run. And so it's very important that now we start understanding what are those applications, how do those applications want to interact now with the infrastructure? So we combine all of these things and we get a much different view of what we want the networking to do and how we want to have programmatic access into the entire infrastructure making up the data center. So there's a lot of new terms that now are swirling around in cloud computing. We've just talked about APIs, the application programming interfaces. How does software now interact with the infrastructure? Application orchestration, the applications that are actually of interest in this world are applications that are spread horizontally. They are scaled horizontally. They are run over tens to hundreds to thousands of virtual machines. When you do that, you have to orchestrate how those individual components work together. In fact, there's a lot of talk about if the infrastructure we've heard before about the monitoring becomes really important. What happens when an individual machine runs into problems? And the easiest thing to do is to kill it off and start up another one. Well, obviously, that's not going to work if you have only an application, a one-to-one relationship. The application has to be spread across lots of machines, and you want to be able to design these things for failure, that allowing any individual virtual machine to fail and the application can continue to run. That's really what we mean by elastic computing, is that you can start to dynamically stretch the application, scale it up, scale it down according to load, and have it live through the kinds of failures that you might expect to see. In terms of the infrastructure itself, now how do you operate that kind of a platform? If you're running that data center, we're coming up with this term called DevOps, which really means that now instead of system operators sitting there typing CLIs, or using a GUI, they're actually writing code. They're writing code. We're using code to manage the data center itself. And this becomes a much better way to deal, first of all, with the scale of data center, and you avoid a lot of the human-introduced errors because you can codify policy into code and apply the code for the running of your data center. Again, network virtualization comes into this, and the term software-defined networking is now coming about, which I'll touch upon briefly as well. So let's look at a traditional data center and understand how we sort of got here. In fact, most people today, the applications are written in this kind of stovepipe environment. What I mean by that is that you take your application, the application defines the operating system. The operating system generally defines what is the physical architecture that you deploy that on. And in the beginning, it looks rather nice and highly optimized into that stovepipe all the way down from the application down into the infrastructure. down into which database, what kind of HA failover model you might have. All of these things are built as individual silos. In essence, what you have are microarchitectures for each one of these things. And so at the end of the day, what you really have is a problem for this guy. Because now he's looking at all of these applications across all of these servers, each one of which has actually very poor overall utilization. It's very inflexible. You can't move one application from one of these microarchitectures to another. And so this is really the problem with traditional kinds of data center approaches. And you end up with this poor utilization and these stovepiped applications that make it very expensive, and the complexity starts to grow with the number of applications. Because now you have to have people trained, and they have to understand each one of these architectures going forward, which makes that difficult. Instead, when people are looking at how they want to design their data centers going forward, they're starting to think about what they want as a cloud infrastructure service. And by doing this, what we're really doing as a computer scientist, I like the model, we are separating out the applications from the underlying infrastructure and allowing them to evolve independently. The applications are all now virtualized on virtual machines, meaning that they are now independent of the resources that they use in the data center itself. In fact, when you do this, I also urge CIOs that I talk to start to think about organizational changes to support this model. Instead of having your IT organization organized around each one of these applications, you should horizontally structure your IT organization. Have some part of the organization running your cloud. Just like Amazon's cloud, they are gold on providing the most efficient and lowest cost virtual machine per hour, virtual storage block per year. Those are the goals. They stay out of the application space. And what you will find is that they will quickly automate everything to reduce their own work. And they will make it so that they can really focus on the things such as capacity planning, overall utilization, overall resiliency of this infrastructure. Now, you still have perhaps a responsibility for running your financial apps, your marketing apps, and everything else, but now have another team do that, because that will be very varied. Some organizations, particularly like your engineering organization, would prefer you not to have anything to do. Just give them virtual machines. They can develop their applications and they're happy. So it becomes very different in terms of how you are managing applications from managing this cloud service. And I think in the last couple of years, we've seen a tremendous growth in terms of private clouds. And that's because people realize they can actually move to this common kind of model and very efficiently start to run their infrastructure. So how do we go about building this kind of infrastructure? Well, I think the place to look is really what the large web companies have been doing. Anybody who's been working on very large web infrastructure knows that it's a very different approach than enterprise. Enterprise applications traditionally have been built for vertically scaling. You get larger and larger SMPs, you have a single host, you perhaps fail over and you're running an active-active or active-passive kind of environment. And this is because these enterprise apps are serving employees. And there are some very large businesses for sure, but the number of employees you're having to serve with that application generally is pretty bounded and not growing very fast. These also generally tend to be transactional. And so they make very heavy use of traditional kind of databases. And they're largely built on commercial software. The software industry has been supplying these things very effectively. In the web, things have been very different. Websites don't know. They may have to scale 100x in a year in terms of their capabilities. So they design applications to be a scale-out architecture, running, like I said, over tens to hundreds to thousands of hosts or virtual machines. When you're designing at that scale, failure of individual components is inevitable. It will happen all the time. It'll happen repeatedly, and your applications have to be able to live through that, survive through the individual component failures of hosts or databases or services. So you start to think about infrastructure pools instead of these islands. It's no more stovepipe. You need to have a pool of infrastructure you can apply to these applications, and that you're going to have the management through software. This allows you to have one system administrator for 1,000 servers. There's a very different approach here, and the other thing is that it's largely done using open source components. And this is because the commercial software industry really hasn't targeted this area. And so whenever there's a void in the market, People will get together, and this is what prompts the tremendous growth, I think, in terms of open source software. So open source itself, I think, is having a big impact now in cloud. And in fact, many are now looking at this and saying, this is where the standard cloud infrastructure will be defined. This is where the next standards will be generated, instead of out of standards bodies, people working sort of in the abstract, through the code itself, through these large-scale open source projects. And this means that as an industry, we get together and we get to discuss this, and through the open source collaboration tools, be able to make contributions of code so that we can evolve the platform that we all feel that we need moving forward. I know that there's been several talks at this conference on OpenStack, and so I'm not going to go into great depth here, but OpenStack is yet a great example of this. It really is designed it is an open source project designed to allow anybody to build their own public or private cloud. So that if you are thinking of being a service provider, or you want to run it in-house for your engineering organization, or you want to run your entire data center on a cloud computing model, OpenStack is the software that will allow you to do that. It's very young. It was started in July 2010, initially with contributions from NASA Ames, where they contributed the computing service, and from Rackspace, which was a file service. And now it's moved to a foundation-led organization. There's over 180 companies now participating. The way to think about OpenStack, and the reason why it's called a stack, it really is a set of loosely coupled services. So rather than being a monolithic, fully integrated software platform for cloud computing, it's specifically designed to be a set of loosely coupled services. This allows us to compose this into a cloud platform. This also allows us to focus a lot of our efforts on these individual services as we apply engineering resources to this. And of course, they talk to each other to produce the ultimate cloud platform. So a request will come in, for example, for the compute service to spin up a virtual machine. It will call upon the identity service to perform authorization and everything else, and it then may also talk into the networking service to bring up that virtual machine. So this allows us also to extend this, and so this is where participations by lots of other companies who are specializing in one or more of these areas can participate as we grow the number of services going forward. This just shows a kind of adoption in terms of participating companies for OpenStack today. We had started originally, around 30 or 40 companies that were getting together, and we've quickly grown to over 200 companies that are participating. OpenStack.org, if you take a look at it, you will not only see that, but you'll also see that now as we move to a foundation, and I really applaud Rackspace, which had most of the intellectual property and websites and development teams associated with this, and moving that over into a foundation. So now we've started a foundation. We have platinum members, gold members, and individual members, 24 of which make up now a board of directors for the OpenStack Foundation, whose purpose is primarily to drive now the adoption of OpenStack and the development of the ecosystem, whereby we're keeping the technical committees of OpenStack itself separate from the foundation so that they are able to work still in the meritocracy of the code itself. At the same time, now we're beginning to see new companies coming into this as well, and I wanted to point out just one of them, which is Comcast. Comcast is looking to adopt OpenStack for its next generation applications. So this is how they're looking at, their applications serve millions and millions of consumers. And they're looking that they need this kind of cloud platform. So they aren't necessarily looking to compete with Amazon offering up virtual machines. It's their core applications they're looking to move on to this. Inside of Cisco today, WebEx, we're having the same approach. As we're rolling out new WebEx services, we're building that on top of an OpenStack platform. So this is, again, an example of how you're using essentially a on-premise private cloud as the fastest, most effective way to rapidly develop and deploy applications that can serve a very, very large number of consumers out there. So this is, in essence, the growth, I think, of the consumer cloud that we see coming from companies like Comcast and WebEx and others. So let's talk about applications. If you're like me, applications almost always start on a whiteboard. You get together with a couple of developers and you start talking about, well, this is how we might logically like to have this application. We need a couple of web servers, we probably need a firewall and an app server in the back end, and we start with these logical diagrams. They sometimes start to get more and more complex as we say, how do these applications start to scale? And an application architecture starts to become apparent. I mean, it's represented, it does have a topology associated with this. I would like to have front end that are connected to the internet, the true cloud, which is the internet from days of old. And they are then interacting directly with the consumers, whereas my database, I would prefer not to be routable from the internet. It just generally is a bad idea to have that be routable. So you want to be able to use some of the topological constraints here and security constraints and networking and everything else to do that kind of separation. And you want to insert other services in between the different layers, load balancing services, or traffic distribution services, memcached services, things such as that. So this is what are the technologies that are really present in a data center, and application guys want to have nothing to do with this. So the challenge really is, how do we take advantage of the capabilities that are in this data center without exposing this kind of complexity? So stated very simply, so what is the network abstraction that we need that makes sense for developers? Not network system admins, but for application developers, without bringing all of that complexity up into the application world. This is where we were essentially about 1.5 years ago in OpenStack, where we were looking at this problem. And we're saying, well, let's think about it in terms of the abstractions and the layers and interfaces. On the compute service, the primary core abstraction there is a virtual machine. We have an API that says launch a virtual machine with so much memory, so much disk, using this specific image that we want launched on that. And then you can do different operations on that virtual machine. The primary abstraction there is a virtual machine. With storage, the primary abstraction is either a block of storage or a file or an object. Again, those are the primary abstractions, and allows you to make a very simple API. Store this blob, store this object, retrieve this object. So what about networks? It turns out to be it actually follows a very similar model. In a network, the core abstraction, working with about 12 to 14 other companies we came up with over several days of discussion, was that of a virtual isolated network segment. In essence, a line or a wire that we would be able to now add virtual machines to connect this virtual machine to this network that I created. This is now a tenant network. How this maps into the physical world, we can leave aside. From the tenant or the application perspective, it would like to take that diagram that you saw on that whiteboard and as quickly and as most directly represent that in the actual infrastructure. So you can create a virtual network. You can attach a virtual machine to that network. You can actually create a port on that network to attach the virtual machine. And now over time, we can then start to add those other kinds of capabilities. So we called the service quantum, meaning it would be the most basic elemental part of networking. And over time, we can now add routing, IP address management, service attachment, and everything else. To make this work in the real world, we have to have the interfaces, of course, into the physical environment. At the end of the day, bits have to travel over wires. So we designed the architecture such that the top layer is a common set of APIs. The bottom layer, think of it almost like device drivers, plugs into the different implementations according to the different vendors' networking environments you might find there. And at the same time, allow API extensions. So particular capabilities that are available in that infrastructure could again be available to the application designers themselves. So in many ways, we took what is a traditional model of cloud computing, which is a compute service, a storage service, and perhaps identity and other things, and what we added was networking. So that in this model now, network as a service, networking as a service, becomes a first-class citizen, a peer of compute and storage. And in many ways, particularly from a computer science point of view, now I can actually think about my virtual environment that I want to be able to create a virtual data center that has these essential elements of computing, storage, and networking available. This allows this kind of connection now between the world of applications, which is up at the top, where in a multi-tenant environment, you want to think about your own logical data center that you have, either at the application level or at the tenant or customer level. And the different layers now translate that into the physical infrastructure as well. And the providers now, these cloud services, can also start to think about developing services. Some of those are traditional services around firewalls, load balancers, elastic load balancers, as services that can get on top of this and then provide it into the customers themselves. And we can start to take advantage of the variety of infrastructure and technologies that are available in the networking layers below. So as I mentioned before, networking is changing a lot. Now, as it changes, there's lots of other capabilities now that you want to be able to expose. So for massively scalable applications, they may want to talk directly through software APIs into some of the more programmatic aspects of the network so that they can accomplish their jobs. Whereas others will be built upon a cloud infrastructure which will allow multi-tenant applications to take advantage of the same kind of infrastructure. So in many ways, I think about APIs as enabling a conversation between two different layers. In this case, between an application layer and the infrastructure layer. The application saying, I would like to do the following. I would like to be able to set up a network optimized for streaming media because I'm going to push large video files out through this. Now, the underlying infrastructure then can say, that's what the application is trying to do, and it will set up the appropriate infrastructure. At the same time, what we'd like to be able to do is create that two-way conversation. We'd like to be able to, as we saw before in the talk, networking was kind of difficult to get performance information out of, particularly end-to-end performance all the way out to the customer device. But if we start thinking about these APIs as creating that conversation with the network, we will come up with the mechanisms that allow you to query the network about how it's doing. What is the next hop latency that you might see? You might want to see the entire path of next hop latencies. You might want to see a lot of different information that you can get and analytics out of the network. And so it's not just configuring things, it's actually using information that we can get out of the network itself so you can start to move towards a policy-driven approach towards doing this. Many of these now are starting to talk about SDN, OpenFlow, and other ways of programming the network. And this cuts across a lot of where it originated was in academia, largely in Stanford and other areas where computer scientists were trying to say, how can I make tests? How can I use the network as a laboratory without disrupting everything? So can I create slices of the network that allow me to experiment with new protocols and everything else like that with the same shared network that's handling all of my university traffic? We're seeing this done in massively scalable data centers where they have very different needs and how they would like to see the network behave. Cloud, as I mentioned before, is largely supporting the kind of concepts around multi-tenancy. And so as we're moving forward, Cisco has been heavily involved in something that we've been calling the open network environment, Cisco One. And this is taking a number of those different concepts from the platform APIs, where you can write applications that will directly talk to the network operating system, and being able to get information from that, and also to configure it to SDN, where we have controllers, where you now want to have some entity, some software entity, managing a whole lot of these, and providing kind of a uniform view across some segment of the network. And then virtual overlays, where we create these logical overlays or tunnels to be able to express these virtual tenant networks for the applications themselves. So on top of this now, this is where we tie both what's going on in SDN and what's going on in cloud computing together. And that's through this network service called Quantum. And this is why what you'll see in a lot of the OpenStack work, there's a large and growing number of OpenFlow controllers that are going into that, virtual network controllers going into that, and we're ourselves are supplying Cisco plugins that allow you to get to the richness of our one environment. So Cisco's involvement with OpenStack has really been in these three areas. First and foremost, it's really been contributing back into the community so that we can influence the direction of cloud computing going forward. And in terms of that, it's been focused primarily on quantum, but increasingly we're looking now at things such as network-aware scheduling. Because the compute service, where it places VMs, become important in terms of the overall infrastructure. And other kinds of services that start to take place there. And then working with a lot of our different customers who have very unique needs in terms of how they're viewing this common cloud platform and how they plan on using it. So use cases that we're getting from a customer base driving a lot of the innovation. So most recently, down in San Diego at the last Design Summit, we introduced something called our OpenStack Cisco Edition, which is also now a deployment environment. So it's one thing to deploy these individual services, but if you're going to put that in production, how do you do things such as high availability? How do you make sure that you can survive failures? So a lot of that is how do you orchestrate the system with a lot of scripts. We partnered with Puppet Labs to do a lot of the scripting so you can have a deployment environment, and that's what was available in that. And we also started to integrate some of Cisco's other properties. We mentioned application orchestration. So when the apps that sit above this, they also need orchestration. You need to be able to create, if you're putting up an app which is, let's say, for a big call center. Well, as new customers come on, you may need to run new call managers into that, being able to scale that application up and down. So that's where we have something called intelligent automation for cloud, and we've made plugins now for OpenStack and for EC2 and for Citrix, Red Hat, and Microsoft. So this is now a common way to orchestrate applications across many, many clouds. So lastly, I just want to say, what we're seeing now is the layer cake of cloud computing being built. Starting with virtualization layer, putting in the core cloud platforms, building out a lot of the additional services that you see, such as elastic load balancers, scalable databases, Cassandra, other kinds of services that can sit on top of that, all in the goal of making it easier for application developers to develop scalable applications. Obviously, not everybody should have to re-implement Cassandra or have to re-implement a scalable object store. Instead, those start to become services in a multi-tenant environment that makes it easier for you to build these scalable applications. So with trying to leave just a couple minutes left here for questions, cloud computing is changing. And all of us should be asking ourselves, I think, what are the services that will accelerate the application development and deployment? That's the main purpose. How do we speed up the development of applications and the deployment of applications and the scale of applications? What are the abstractions? We've talked about a few of them today. And what do we want to keep hidden and so we avoid the complexity of the whole data center infrastructure from moving up into the application world? So those abstractions are very important. The APIs are very important. And that how do we build in this capability for future innovation in this kind of infrastructure? So with that, I think there's a couple minutes left. I'd be happy to take a few questions.
There certainly is, and here comes the first one.
My question is about complexity. I will add Turing and Gödel to your pictures of Darwin and Gordon and, of course, Adam Smith. Basically, the Turing machine is what we use today, and Gödel's theorem basically says that there is a management complexity that you cannot avoid because who manages the managers? So essentially, that's what we are stuck here with is a large number of managers managing managers and managers to manage managers.
It's turtles all the way down.
Exactly, Gödel all the way down. So unless you address the Turing computing model and the management at the abstraction layer, at the compute layer, all the stuff that you do is not going to ever succeed because it's really building a lot of Turing cathedrals on quicksand. So how do you address that fundamental problem and get back the simplicity? Because right now, we have layers and layers and layers of management software. Nobody knows. It's all OpenStack, and lots of people have written. But Gödel's theorem says that we can't develop our way out of complexity. So I think there is a better way to look at it is actually look at the management of the Turing machine and give fundamental abstractions which are really recursive so that it's like a network model. So for example, we do that in telephony.
Can we get to a question just so I can, yeah, I would agree. Let me even generalize that. It's not just Turing machine making this better. It's better design. And I think better design actually starts with understanding the most important abstractions, the primitives, and then nothing beats good design. And you need great design at all layers.
There's a shorter question over there.
Yeah, thank you. I really like your idea of the programmable network as an abstraction. I think that's very important as we move towards software-defined networking. One of the things that was missing out of this discussion was around security and security services that should be also built into this. Any comments?
Oh, I absolutely agree. Security is an essential component of this. And it's been difficult, though, in my own mind, to understand how do we bake it, how do we build it in such a way that it's not this afterthought. That it seems like we need to understand when we're creating these networks themselves, what are the security properties of the network? So you don't just say create a network and then you say apply these policies. Instead, create a network that enforces the following policy. That is, I think, where we want to end up. And I agree with you. I mean, we haven't gone into that depth, but I would hope that by having a community-driven effort around how we make these network services, we can start to get some of those ideas injected into it.
Question right from the back, proving that Lou's penetrated further than any other speaker. Please stand, because he'll never see you.
Hi.
There you go.
Oh, sorry. So within the layer cake you presented earlier, do you think that the bottom layers are ready to support all the innovation in the top in the applications yet? Or do you think we're going to see, that it's already ready and that we're ready for more innovation up top?
So the question is, in this kind of layer cake, are the lower layers ready to support the upper layers? I think the whole reason that we have layers, that's why we have, for example, TCP/IP, you're building reliable protocol on an unreliable infrastructure. So yes, of course it's ready. I think a deeper question is, if we do these layers right, will we allow innovation at the lower layers in areas that we hadn't even anticipated? I was part of the early Java team at Sun, and that was one of our mantras. We wanted to create a new layer, new abstract machine that would allow new processor innovation. So my hope is that when we move to these layers, not only will they have the capabilities, but they will expand their capabilities over time through innovation.
Two more questions for Cisco's cloud CTO. Starting with you, sir.
Thanks so much for the presentation. I think it was brilliant. My question was, are these architectures primarily limited to a specific data center, or do you think that these can be extended across geographically and just treat data centers as a resource, and abstracted across?
That's a great question. In no way should we be thinking that this is a single data center architecture. I think it is much more interesting as we're looking, these architectures, either you talk about them as having multiple domains, or in OpenStack we're talking about them as cells. We have to start taking the WAN into account. One of the things, for example, we are looking at with Quantum, for example, is a networking protocol called Lisp. Not the programming language, but it's actually a network abstraction that separates out location from identity. So things actually, you can think of them having envelopes where you have an addressee, who you want to send the letter to, and the separate part is where the address actually is. And that allows us to go build clouds across multiple data centers, across the WAN. It's a very good point that we should not be limiting this to a single data center. I don't think that's the future. It's multiple data centers.
Last question, also right from the back there.
From a market adoption standpoint, you take out your crystal ball, and OpenStack, it gets adopted, contributed, but from a practical usability standpoint, what do you see as a timeline for the availability of open network for the general public to use?
The timeline is what I always get wrong. I'm always more optimistic, I think, than the penetration or adoption by the rest of the world. But I think it's moving very quickly, and I've been very much surprised. I think there's a lot of talk is OpenStack hype, where does it sit in the Gartner hype, adoption curve, or we've crossed the chasm. The thing that I think that will really propel it forward is that, just like with the whole network effect of fax machines, as more and more providers come up with OpenStack, that'll create more and more demand for OpenStack, because now customers will be able to have choice. They can be able to go to one service provider running their application and running OpenStack, move it to another one. So we'll start to see a cloud of OpenStack deployments happening, and that I think will fuel greater and greater adoption, get the cycle going.
There we are. A very uplifting note, Lou, on which to finish. Let's give it up, please, thunderously, for Luke Tucker, CTO at Cisco.